Hello and welcome to another Algebra 1 video by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 3 on properties of systems and their solutions. That's a mouthful. And what does it even mean? Well, today what we're going to be doing is we're going to be looking at systems a little bit more in depth and see what kind of manipulations we can do to a system of equations and still have the same solutions. Now this is all a setup to our next method of how to solve systems. So far we've seen how to solve a system using graphical methods by finding the intersection points, also by substitution, by substituting one equation into the other in order to eliminate a variable. Eventually, in the next lesson, we're going to be driving at what's called the elimination method for solving a system, and we'll even see that right towards the end of this lesson. But first, we want to explore how systems behave when we play around with the equations. So let's get into it. Take a look at the properties of systems and their solutions. So the properties of systems. Systems of equations play by certain rules that we call properties. These are things that are always true about the systems and their solutions. So let's try to explore some of those properties in the first exercise. Exercise number 1. Consider the system shown at the right and its solution 1, 5. 4x plus 2y equals 14. And x minus y equals negative 4. Letter A, show that x equals 1 and y equals 5 is a solution to the system of equations. All right, awesome. So we have definitely done this quite a few times already. I'd like you to pause the video and show that x equals 1, y equals 5 is a solution to the system shown. All right, let's do it. So what we have to do is we have to show that both equations are true when x is 1 and y is 5. All right, so my first one, 4 times 1 plus 2 times 5 is equal to 14. 4 plus 10 is equal to 14. And 14 is equal to 14. Awesome, true, right? My next one is x minus y is equal to negative 4, and that's even quicker. Negative 4 is equal to negative 4, and that's also true. All right, great. So it must be a solution to the system because it makes both equations true. Now, before we move on, I do want to point out something about this system that's a little bit different than the ones that we've been looking at lately. Notice in this system, both of the variables in both equations are on the left side of the equation. Many of the systems that we worked on from now on are going to look kind of like that. In other words, there isn't going to be a variable that's all isolated and by itself. All right, that being said, let's take a look at letter B. Find the sum of the two equations. Is the point 1, 5 a solution to this new equation? Justify your yes, no response. All right, great. So I want to find the sum of these two equations. What does that mean exactly? Well, what it means is that I want to add the left side to the left side and the right side to the right side. Now, the way that I like doing this is I like to literally stack the equations one on top of another. So I write this one, and I write this one, and I'm going to add the two equations together. And what's great about this is I can just combine like terms. I'm going to get 4x plus x, which is 5x, and then I'm going to get 2y plus a negative y is just a positive 1y, and then I'm going to have 14 plus negative 4, which is a positive 10. All right, remember I'm adding these, not subtracting these. So when I add the two equations together, I get 5x plus y is equal to 10. Simple enough. And I should be able to just see that right here. You know, 4x plus x is 5x, 2y plus negative y, or if you want to think about it as 2y minus y, however you want to think about it, 2y plus negative y is positive 1y, and 14 plus negative 4 is positive 10. So one thing they asked us to do is find the sum. Then they asked, is the point 1, 5 a solution to this new equation? Well, let's do that together, right? That's easy enough. I just take that point and I substitute it into my new equation, 1 for x, 5 for y, and I get 5 plus 5 is equal to 10, 10 is equal to 10, and that's a big yes. Now, let's be very clear about that, right? What that says is if I've got a point that's a solution to a system of equations, It's also a solution to an equation produced when I add the two equations together. So when I add two equations of a system together, the solution remains the solution, right? It doesn't change. Very important. Let's take a look at a little bit more in terms of properties. Letter C. Multiply both sides of the second equation by 2 in order to get an equivalent equation. Is the point 1, 5 a solution to this new equation? Justify your yes/no response. All right, so even though I've got both of these equations written down, I just am saying, look, if I take this second equation and I multiply both sides of the equation by 2, will the point 1, 5 still be a solution to that equation? Well, let's do this together. All right, so if I take that second equation and I multiply the left side by 2, and I multiply the right side by 2, I get the equation 2x minus 2y, got to make sure to distribute, equals -8. Okay? Now I want to see if 1, 5 is still a solution to this equation. Well, again, easy enough to do, right? 2 times 1 minus 2 times 5 equals -8. 2 minus 10 equals -8. And -8 equals -8. Yes. Right? Now, by the way, that one shouldn't have been a surprise at all, right? Because multiplying both sides of an equation by a constant like 2, that is a property of equality, right? And the whole point of the properties of equality, right, which we've looked at before, is that properties of equality do not change the solutions to an equation. So what do I know now? I know I can take two equations in a system and add them together, and it doesn't change their solutions. Or I could take one of the equations and multiply both sides by a given number, and it still doesn't change whether or not something is a solution to that equation. Now let's take a look at letter D. Take the equation you found in C and add it to the first equation. What happens? How does this allow us to now solve for the variable x? Do so, what do you find? All right, so again, let's make sure you understand kind of almost like where we're headed before we start traveling there. Right now we know if we add two equations together, we still get the same solution. Or if we multiply both sides of the equations by the same number, we still get the same solution. So what I'd like to do now, or what this problem tells me now, is to take the first equation, 4x plus 2y equals 14, and add it to the new equation that I produced in letter C, 2x minus 2y is equal to -8. Right? So when I add these two together, 4x plus 2x is 6x, and now this is very important. Positive 2y and negative 2y, when they add together, is just 0. 14 plus -8 is positive 6. So, what happens? Well, when I added those two equations together, because 2y and negative 2y were opposites, the y was eliminated. All right, so what happens? Y was eliminated. Now, what's really awesome is that it leaves me with an equation that only has an x in it. And because it's only got an x in it, I can solve it for x. So let's do that. Let's solve it for x. 6x plus 0 is equal to 6. Well, 6x plus 0 is just 6x. I can now divide by 6 on both sides, and look at that. I get x equals 1. Now, I know. We already knew that the point 1, 5 was a solution to this system. So it's not a shock that I got x equals 1. But this is the first time that I actually used algebra to figure out that x had to be 1 as opposed to just knowing that x was 1. Now let's take a look at letter E. Once you know the value of x, how can you find the value of y? Well, right, so now I know the value of x is 1. How can I find the value of y? Well, I can use the principle of substitution, take x equals 1 and substitute it into either one of these two equations to figure out the value of y. So how can I find the value of y? substitute x into either equation. And in fact, let's do that. Because it doesn't really make too much of a difference to me, I'm going to substitute it into the first equation. 4 times 1 plus 2y is equal to 14. I get 4 plus 2y is equal to 14. Subtract a 4 from both sides. That'll give me 2y is equal to 14 minus 4, which is 10. And divided by 2, and I get y is equal to 5. Again, I get it, right? We already knew 1 comma 5 was a solution. The point here is, right, I was able to use those properties to eliminate one of the variables by just adding two equations together. And then once I eliminated a variable, I could solve for that variable's value, substitute it into one of the two original equations, and find the other variable value. This is what we're going to eventually call the method of elimination. And it's really kind of a cool method to solving systems of equations that is sort of an alternative to either solving them graphically or solving them by substitution. Now, the previous exercise illustrates the most important properties of solutions to systems of equations. So let's take a look at those. Solutions to systems of equations remain solutions if properties of equality are used to rewrite either of the equations, and the equations are added or subtracted, or any rewrite is added or subtracted. All right, so let's distill that a little bit, right? So in other words, systems have this great property where if you take either one of the equations and you, let's say, multiply both sides by a given number, or divide both sides by a given number, add, subtract from both sides, but let's be honest, most of the time it's going to be multiplying both sides by a given number, then the solutions still remain the solutions, because that's just a property of equality. The other one is if I add or subtract the two equations of a system, or maybe an equation that I've modified using a property of equality from one, then again the solutions still remain the solutions. Okay? Let's play around with that a little bit. Very, very important. Exercise number 2. Consider the system shown to the right. 4x minus 3y equals 15, and 3x plus 2y equals 7. Letter A, show that the point 3 comma negative 1 is a solution to the system. Well, we've certainly done this a bunch, so pause the video now and show me that the point 3 comma 1 is a solution to this system. All right, let's go through it. Well, first things first, I'll substitute it into that first equation. So I'll put in 3 for x, negative 1 for y. That'll be 12 plus 3, right? Negative 3 times negative 1 is equal to 15. 15 equals 15, that's true, right? Now I'll substitute it into the other equation. 3x plus 2y is equal to 7. 3 times 3 plus 2 times negative 1 is equal to 7. 3 times 3 is 9. 2 times negative 1 is negative 2. 9 plus negative 2 is 7. 7 equals 7. That's also true. All right, so that point is definitely a solution because it makes both of those equations true. Now let's play around a little bit with those properties of systems and their solutions. All right, I need to keep that on there. Let's take a look at letter B. The point 3 comma negative 1 will be a solution to the system shown below. How can you determine this without substituting the point in? All right, so in other words, how can I tell that 3 comma negative 1 will definitely be a solution to this system without plugging it in? And as a suggestion, take a look at this system and compare it closely to the original system. Pause the video now and see if you can figure it out. All right, well, it's pretty simple. If you look at this first equation, 4x minus 3y equals 15, and this equation, 8x minus 6y equals 30, this equation is algebraically equivalent to this equation after both sides have been multiplied by 2. This equation, 9x plus 6y equals 21, is the same as the second equation when both sides have been multiplied by 3, right? So this system can be produced by multiplying the first equation by 2 on both sides, and the second equation by 3 on both sides. All right, so in other words, I just used the properties of equality, multiplied both sides of that first equation by 2, both sides of that second equation by 3, so I get these two equations that look very different than the original two, but in fact must have the same solutions because a property of equality was just used to produce them from the original. All right, let's take a look at letter C. What happens when you add these two equations together? Why does this let you solve for x? All right, well, play around with this. Like add the two equations together and solve for x. Pause the video now. All right, well, this is really cool. So what I'm going to do, right, is I've got 8x minus 6y is equal to 30, and 9x plus 6y is equal to 21. When I add these two together, 8x plus 9x is 17x, but when I add these two together, right, negative 6y plus 6y, I just get 0. Obviously, 30 plus 21 is just 51. So yet again, what I end up getting when I've done that particular manipulation is I get these what are called additive opposites. Negative 6y and positive 6y, when added together, eliminate the y variable. They just go away. Negative 6y plus 6y, add them together and you get 0. And because the y is eliminated, I can now easily solve for x, right? I've got 17x is equal to 51. That's an interesting look on that 17x. I can divide both sides by 17. 51 divided by 17 might not be obvious, but it's equal to 3. All right. Now the cool thing is, right, I can use the value from x, from C, to determine the value of y. How do I do that? Well, I take that value of x and I plug it either into the x in the first one or the x of the second one, and I solve for y. Pause the video now and choose one of those two equations to substitute x into and solve for y. All right, well, just to kind of vary it up, I'm going to plug it into the first equation this time. So I'm going to take that x equals 3. I'm going to plug it up into here. You might say, well, why don't you plug it into one of those two newer equations? And you actually could. There'd be nothing wrong with that. But I always like to go back to the original equations. 4 times 3 is 12. Minus 3 times y is 15. Move that away. Subtract 12 from both sides. Don't lose that negative off the y. Negative 3y is equal to 3. Divide both sides by negative 3. 3 divided by negative 3 is negative 1. And again, we knew that up front, right? I told you right up front, show that the point 3 comma negative 1 was a solution to the system. All right, you can almost see the technique developing, right? We'd like to be able to take those two equations, add them together, and have one of the variables cancel out, right? Now, it's only going to cancel out when we add them together if we've got opposites there. In this original system, we don't have any opposites. If I had added these together, I'd get 4x plus 3x is 7x. Negative 3y plus 2y would be negative 1y. So I'd still have both x's and y's. But I will always be able to manipulate a system by multiplying both sides of one or both of the equations by some number to produce opposites. Once I have those opposites, I can add the equations together to have one variable be eliminated. Now we're going to work a lot more with the method of elimination as we go on, but let's take a look at one more situation. We can use the properties of equality to eliminate one of the two variables. Once we have only one variable left, we can then solve the system. So let's take a look at that in exercise number 3. Solve the system below using the method of elimination. Show the steps in your work and show that your answer is in fact a solution to the system. Okay, well look, ideally, what I'd love to be able to do is just add the two equations together. But let's see what would happen if I did that right now, right? If I added these two equations together, I'd have 2x plus 6x, which would be 8x, 4y plus 3y would be 7y, and 2 plus negative 3 would be negative 1. Now that's a perfectly good equation, but it doesn't do anything for me, all right? Because both of the variables are still there. Both the x is there and the y is there. So, yeah, not great, right? So now I want to start to think to myself, well, how could I multiply, preferably just one of the equations, both sides, to create an opposite of something in the other equation? So maybe I look at that 2x and that 6x. Is there a way that I could make that 2x into a negative 6x, right? And I could. If I multiply both sides of that original equation by negative 3, look what happens, right? I take negative 3 and I multiply 2x plus 4y. Now I got to do it to both sides, right? That's the property of equality. I got to multiply both sides. Distribute that negative 3 through and I'd get negative 6x minus 12y is equal to negative 6. Right? So all I'm doing is multiplying both sides of the first equation by negative 3 in order to get the opposite of that positive 6x. Now you might say, well, why didn't you try to eliminate the y's? Because that kept happening in the other problems. Well, I could. The only problem is it's hard to make a 4y into a negative 3y or a 3y into a negative 4y. In those cases, I might want to multiply both of the equations by numbers to maybe make this one a 12y and that one a negative 12y, something like that. We'll see that a lot in the next lesson. Let's not worry about that now. Now what I'm going to do is I'm going to take this equation and right below it, I'm going to write that second equation that's not altered at all. Okay? And now the beautiful thing is negative 6x and positive 6x cancel. Negative 12y and positive 3y would be negative 9y. And negative 6 plus negative 3 is negative 9. Well, that's convenient. I'll divide both sides by negative 9, and I'll find that y is equal to 1. All right? Now what I can do is I can take the 1, I can plug it into either one of these two equations and figure out what the value of x is. Might as well plug it into the first equation. So when I do that, plug it in here, and maybe give myself that extra space, I'm going to get 2x plus 4 times 1 is equal to 2. 2x plus 4 is equal to 2. Subtract a 4 from both sides. 2x is equal to 2 minus 4, which is negative 2. Divide both sides by 2, and I get x equals negative 1. So my solution is negative 1, comma 1. Now, notice this problem does say, show the steps in your work and show that your answer is in fact a solution to the system, right? Because we don't really know that for certain. Now, to show that this answer is a solution to the system, I got to go back to what I did literally on the first lesson of our systems unit, which is take that point, substitute it into both equations, and make sure it's true. Let's do that real quick, all right? I think I can fit it almost right underneath here, especially if I move the eMath logo out of there. Always a shame, but that's okay. All right, so I'm going to put negative 1 in for x. I'm going to put 1 in for y in the first equation. I get negative 2 plus 4 is equal to 2. Negative 2 plus 4 is 2. 2 equals 2. That's true. Now let's do it in that second equation. 6 times negative 1, come on, 6 times negative 1 plus 3 times 1 is equal to negative 3. 6 times negative 1 is negative 6. 3 times 1 is 3. Negative 6 plus positive 3 is negative 3. Negative 3 equals negative 3. Also true. All right, so just trying to finish out that problem. Always make sure you do everything that the problem asks for, right? Besides using elimination to find the values, we also checked it to make sure they're true. And we're going to get a lot more work with the method of elimination in the next lesson, which is literally called the method of elimination. Then we're going to get even more practice with it in the follow-up lessons when we're going to be solving some word problems using a lot of these techniques that we've had, okay? So don't worry about it too much yet if you're still a little bit uncertain what's going on. The main point of this lesson, let's do that in our summary. The main point of this lesson, right, is we've got these systems. For us, it's just going to be two equations with two unknowns, two equations with two variables in them. And the plain fact is, in order to solve these systems, we can do a variety of algebraic manipulations. The two most important ones for us will be that we can multiply both sides of either equation by the same number, all right, and we can add the equations together. So that gives rise to this technique where we manipulate one equation or both equations so that we have opposites that when we add together, they are eliminated and give us that equation with only one variable in them. It's a really slick technique. We'll get a lot more work with it when we revisit this in the next lesson. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.